So yeah, welcome everyone to today's Beyond the Scope talk. It's actually gonna be our last one of the semester before we take a break for the summer and start up again in the fall. And for today's talk, I'm excited to have Dr. Kat Crispin here talking about analysis with EDS and WDS. Kat did her PhD work at Case Western University, and she's worked at a few different places doing a lot of different microprobe and electron microscopy work, starting at Carnegie Institute of Washington after her degree. And then she worked for quite a while at the Materials Characterization Lab at Penn State, which is where I met her. And with working with her at Penn State, I learned a lot more about the characterization with EDS and her specialty doing wavelength dispersive spectroscopy. And I know Kat just started a new position out at Morgan Advanced Materials, where she's doing a lot of different materials characterization. And another thing about Kat is if she's not in the lab, generally you'll either find her in a cave or probably down her board game cave. We've played quite a few games together. Okay, Kat, I'll let you get started on the talk.
All right, thanks, Dan. Let's see here. Yeah, as Dan mentioned, I have my PhD in geological sciences, actually. I know nothing about rocks, even though it says geology on my degree. I was a mineral physicist and more of a material scientist. I've got expertise in a lot of different instruments, and yeah, as Dan mentioned, you can find me in a cave usually. For my PhD, I did a lot of diffusion work, primarily looking at planetary applications, what's going on in the cores of planets. So I also studied a lot of palisite meteorites. Currently at Morgan, I do research on high-end applications for carbon materials related to industry. So like, for instance, one of the things we work on here is in a motor, you've got carbon brushes that help to pass the current. And we're constantly researching ways to improve those brushes to improve current throughput. The big windmills that you see everywhere, collecting wind energy, a lot of those have our brushes in them. I like to start the talk as kind of giving a historical background for where the physics came from for these high-end instruments that we use to analyze things. So I just want to share some of that background. I love this these pictures here because when they were first figuring out how to create vacuums, a guy named Otto van Guericke, he built the first air pump, and to demonstrate it, he evacuated this huge cylinder and then had teams of horses try to pull it apart, which they couldn't, and that was like kind of like crowd pleasing at the time. In the 1600s, Van Guericke built a frictional electric machine. So it basically had this big, huge sphere that rolled around on some stuff to create sparks. And then they improved that into something that was turned by a crank. And he actually didn't know it, but he invented neon light because it glowed with the electricity flowing through it. And then it was like kind of in the 1700s, it was like the thing to do in royal courts is to set up all kinds of static electricity experiments. So you can see some sketches of some of the crazy things they did to make static electricity go from person to person and ring bells and all kinds of things. It was like kind of like high-end magic for the time. But they started getting practical about it in the mid 1700s, and von Muschenbroek he invented what was called a Leyden jar, which was an ability to store the static electricity. So instead of just, creating a spark current going through things, he could actually capture it and create basically this is an early battery. Ben Franklin then expanded on these experiments. We all know about the kite, but he did a lot with the Leyden jars too. And so he would collect a lot of this static electricity that he found into Leyden jars. So we actually owe a lot to Ben Franklin, because he's the one that first described it. It was the early beginnings of understanding what electrons did. He's the one that is responsible for calling the flow direction positive, which is kind of backwards if you think about it, but we all do that now because Ben Franklin started it. And then he observed how pointed objects draws off the electricity very nicely. And that's actually the foundation of where our electron instruments come from. Is we currently, you can see on the right there what one of these anodes looks like, with the current flowing down. In this case, it's a tungsten tip drawing off the electrons down to the anode, and being able to see small items then. The next thing that happened was people came up with cathode ray tubes, which were used for a very long time, hundreds of years, history of cathode rays. They could be influenced by magnets, as you see in the bottom right. And they did a lot of experiments with these, and that went into a lot of the early electronic equipment. So in 1897, J.J. Thomson, he confirmed that these cathode rays that they're actually seeing are actually electrons flowing. And he's the one that figured out that they transport negative charge and they're deflected by electric fields and they travel slower than light. Fitzgerald's the one that actually called them electrons the first time. And then the interesting thing is, so Thomson, he got the Nobel Prize in 1906 for proving that the electron is a particle, but his son got the Nobel Prize in Physics in 1937 for showing the electron as a wave. And that's what we all know today. It behaves as both a particle and a wave. And it was responsible for a father and son duo that came up with that. Then we've got the discovery of X-rays, and we've got William Crookes is the first person who noticed that something weird was happening when he stored his photographic plates next to his cathode ray tubes, and he was getting this weird fogging. But it wasn't until Röntgen was the one that figured out that the bremsstrahlung in the cathode rays were actually producing X-rays. So he actually got the first Nobel Prize in Physics in 1901. The famous image on the right is of, depends on who you read, it's either his assistant's hand or his wife's hand that he imaged with X-rays. That had an immediate effect. They immediately saw the uses of X-rays, and so the medical profession was the first to jump on this, and they were able to find like broken needles embedded in hands and things like that. And everyone thought this was the coolest thing in the world, so they started experimenting with X-rays, not realizing the danger. And so the number of assistants that developed cancer and had hands amputated and everything due to exposure to X-rays was quite a few. And we care about X-rays because that's the basis for all of our characterization methods in WDS and EDS. That's a list of all of some of the things that we know about X-rays, and it's very useful for a lot of applications. They're also considered both particles and waves. So they consist of small packets of photons. They are produced by accelerating electrons in a vacuum and colliding them with a target. You get continuous background bremsstrahlung, along with occurrence of sharp lines, which are the characteristic X-rays that we use. And then there's a cutoff of continuum at short wavelengths. They have no mass and no charge versus electrons, which do. So don't get them confused. Electrons have no mass and no charge, but electrons have a charge and a small mass. X-rays can generate other X-rays, but no bremsstrahlung is produced through that effect. So then in 1912, von Laue, Friedrich, and Knipping, they're the ones that observed X-ray diffraction, got the Nobel Prize. Beatty was the one that showed that it produced two different radiations. And then Bragg built the first X-ray spectrometer. He used just general table salt and used it to resolve platinum X-rays. Bragg's law is the basis for all of our ability to calculate characteristic X-rays and which elements they apply to. It's a foundation for both XRD and WDS and EDS. So then they built an early box. Kirchhoff and Bunsen showed that they could actually see incandescent light based upon the characteristics of that substance. So they started cataloging all kinds of stuff that they started throwing in this box to figure out what the wavelengths looked like. And on the right, you can see a list of some of the ones that they described in their work. So characteristic X-rays, how are they actually produced from a physics standpoint? You've got an incoming electron that comes in and it knocks off an electron from the inner shell of an atom. And as that goes out, these atoms cannot stand to have a hole in their inner shell. And so one of the electrons from a shell further out will drop into that hole in order to fill that void. And when that happens, it has to shed energy. So when it sheds energy, that comes off in the form of an X-ray. And those X-rays are characteristic not only of the atom, but also of the shell that is involved. Most of the time we're analyzing things from the K or L shells, but we can also get into great detail if we had enough resolution to figure out specifically which electron is coming off of which shell. So then Barkla discovered that they have constant absorption, and that is it decreases with increasing atomic weight. So he started out a rough chart to show that these things correspond. And he found out that heavier elements typically have two of these constant absorption coefficients, which is because they have more shells, so they have both K and L shells. He got the Nobel Prize for that in 1917. Then Mosley came along and he found the regular relationship between the atomic number and the characteristic X-ray. And he constructed the very first X-ray spectrometer, where he was able to use an X-ray tube, change the targets, and use photographic plates in order to image these. And in 1914, the figure at the right is his first quote unquote electron probe analysis of a man-made alloy. And Mosley was a really smart guy. He's the one that figured out that the wavelengths of these characteristic X-rays varied inversely with their atomic number. And so he was able to plot up a lot of data and figure out where most of the elements that were known at the time plotted up and showed the linear relationship. Unfortunately, he was killed at Gallipoli in World War I. And the quote from Isaac Asimov I love is that in view of what he might still have accomplished, because he was only 27 when he died, his death may have been the most costly single death of the war. And that's very true, because his research is the basis for all of how we analyze things today. And some other people came along and were able to find some of the gaps in his charts there on the right, and were able to find elements that were missing at the time. So then we move into actually building these things. And I love the picture on the left. It looks like the mad scientist. But Ruska was the first one to build a magnetic electron lens, and that's actually the same design we use today. So any TEM or SEM that you may use basically uses the same design that Ruska came up with in 1931. The first TEM was built by him in 1933. And that's what you see on the left is a picture of that. He did get a Nobel Prize eventually for that also. And then because he was working with Siemens, Siemens was the company that started to deliver electron microscopes. And these were TEMs then. So that's how we started. Then Hillier and Prebys built an electron microscope capable of magnification of 7,000, which is pretty impressive for that time if you think about it. And then Hillier was hired by RCA to build electron microscopes. And the RCA at the time thought that there'd be a big market for this. So they wanted to start commercializing it. And they filed a patent, and that's the basis of our first really SEMs. And we see that Van Arden built the first scanning electron microscope, but it was bombed during World War II. So Hillier, Zorkin, and Snyder were still working at RCA, and they got the first SEM, which you can see on the right. It was a huge, monstrous instrument at the time. And they were able to use it to magnify surfaces of samples. And then McMullen was the one who built the first SEM like we know today. So Cambridge Instrument Company came along and started commercializing this in 1965. So this is really a relatively new technology. At RCA, Hillier and Baker did build the first electron microprobe, which had an energy loss spectrometer instead of the typical one that looks at characteristic X-rays that we know today. And they patented it, and then RCA decided that commercial applications weren't there, and so they kind of abandoned it. Then along came Castang, and he did his thesis on, he actually built the first electron microprobe. So we call him the father of electron microprobes because all of the science that he put into this project, we actually still follow all of that, the physics of that today. There hasn't been a lot that's been expanded on. And you can see a schematic of his the very first electron microprobe that, I mean, I just can't imagine. For his PhD, he built an electron microprobe and he came up with all the physics of how it works. And that's just truly amazing to me. It seems like more like the basis of, 4 or 5 PhDs, but that's how we got our start doing this. And he did not get a patent for it, which is a shame, but we still think of him as the father of VPMA. And on the right, you can see the first commercial electron microprobe. It was made by Kamika back in 1956. And Kamika pretty much hasn't, I mean, the aesthetics of it changed over the years, but the physics still work exactly the same as it did back in 1956. And then GE started building electron microprobes. The first operating one in the United States was at GE, but then they also abandoned it for commercial production and said there wasn't much of a market. So we need to generate the characteristic X-rays in order to figure out what the material is to characterize it. So what happens when the electron beam hits the surface of a sample, you get off a bunch of different things come off the surface. You get backscattered electrons and secondary electrons that come off, and that's how we do our imaging. You're also emitting cathodoluminescence, some Auger electrons, but the ones that we care about are the characteristic X-rays, and they come, from a little ways down in the sample. So this is more of a bulk technique. It's not a surface technique. And we consider the entire volume that's affected by these, by the electrons interacting as the excitation volume or the activation volume. So when someone asks you like, well, can I look at something that's a couple of nanometers thick? The answer is no, because in order to get the information, it comes actually from deeper than that. So you're really passing through something that's that thin. So this is more of a micron technique rather than it is a nano technique. The interaction volume varies depending upon what the material is that you're looking at and also the accelerating voltage you use. So lighter elements tend to have a larger volume. So things like carbon and aluminum, you get this huge interaction volume, whereas something like gold or silver has very little interaction volume, so you're getting it from closer to the surface. Likewise, if you increase your accelerating voltage, you're going to get deeper into the material. So if you're looking at like thin films, lower accelerating voltage is better so that you only get the thin film rather than getting into the substrate. Two different types of characteristic X-rays are looked at. Wavelength dispersive spectroscopy, that's what an EPMA uses. They collect the X-rays emitted at the correct takeoff angle, which is specific to a particular element. So there's a crystal inside that has defined D spacing. So you're basically using Bragg's law in reverse. You already know the spacing, and you're using that to back out what the proper wavelength is so that you can figure out what element it is. Energy dispersive spectroscopy, on the other hand, is where you basically collect all the X-rays at one time. It gets binned according to the energy, and you look at a histogram of X-rays detected per channel of energy. And most SEMs today have some sort of EDS on them, unless you're just doing plain imaging. But the basic way to figure out characterization of your material is to have an EDS mounted on an SEM. On the left, you can see an example of an EDS spectrum. As you see, there's 4 peaks shown there, 3 of which correspond to iron, 1 of which corresponds to sulfur. And you get an idea of what it is. So EDS is more qualitative. It's telling you what it is and where it is. If you want it to be quantitative and you want to know exactly what the stoichiometry is, you have to use standards and normalizing the beam. Comparisons are made between known standard compositions and the unknown sample composition. So EDS is a great technique for your qualitative analysis, or just giving you a rough estimate of what the composition is. But if you really want to get into the composition, you have to worry about overlaps and things like that. So this is an example of work that I did at Penn State. And they were trying to use EDS to determine the ratio between germanium, arsenic, and selenium in this glass that they made. And as you can see, the 3 different elements overlap very strongly in EDS. So to analyze an EDS, you fit a Gaussian to the peaks. Well, if you look at this, where are you going to fit that Gaussian exactly? Like, what kind of a tail do you have for the arsenic? or what kind of a tail do you have for the germanium? It's really tough to tell because the peaks are right on top of one another. So that's where WDS comes into play. And you can see here, there's a huge difference. So this was done under the same conditions, so the same accelerating voltage, et cetera. And EDS is the red line that you can see, you know, where the peaks are strongly overlapping. But in WDS, the peaks are separated very nicely. So you can very clearly see each peak individually, and you can get an exact stoichiometry for this. So for this project, I was able to do a lot of analysis for them, where I was looking at the ratio of the three elements of interest and telling them very precisely what their composition was. And WDS is really cool because you can even see some of these minor lines. Like I was talking about, certain minor lines correlate to which electron from which shell dropped in to fill that gap. And I can actually pinpoint a lot of those using WDS. So let's talk about some qualitative wave scans and uses for those. So this was a project where they knew there was a contaminant in their material, and they guessed that it was a platinum contaminant. So they wanted to know how much platinum was there that was causing a problem. But when I looked for platinum, I actually didn't find any. So I told them it doesn't have platinum. That's not your contaminant, because there's no peaks where the platinum lines would be. So they wanted to know what it was, if I could tell them that. And I said, yes, I absolutely can. And so I did a full spectrum in order to figure out what the contaminant was. And all of the peaks that you see there are expected, except for that tiny little silicon peak. And that tiny little silicon peak is about 0.05 weight percent. It's very tiny, but it was enough to show that that's where the contamination was coming from. And I told them that it was silicon, and they were overjoyed because they knew exactly where in the process that was being introduced and were able to fix their process. This is some people who were growing germanium fibers, and they wrote a paper that they submitted to a journal showing that it was a pure germanium fiber. And one of the reviewers came back and said, well, how do you know you don't have, you know, a lot of oxygen and carbon in there? Because they're really tough to tell in an EDS, because basically carbon and oxygen are everywhere. So they brought it to me, and I looked at it in the electron microprobe, and I could show them that the count rates for carbon and oxygen were extremely low. So it was just a surface contamination and not part of the fiber itself. And so they were able to pass the review and get the paper published. Some examples of qualitative analysis that you can do in the microprobe. This was a very big company that everyone knows that produces glass. And they could hold the glass up to the light and see that there was like a shimmer of some sort of defect in there. And they wanted to know what it was. Well, when you look at imaging, you don't see a contrast between where the defect was and the glass itself. So it was very hard to locate. So instead I did some line scans in order to figure out what was going on. And it turns out on the right, you can see the line scan that I did. And it turned out that sulfur and iron, so some sort of pyrite, was a large contaminant in the glass. And they were able to find in their process where that was coming in and take care of it. This was some catalysis work that was done. Zeolites, evidently the catalysis reaction is dependent upon the aluminum and silicon ratio. And so I was able to map line scans across in both directions of the zeolites in order to figure out the aluminum silicon ratio for them, so they could tell whether it was going to be sufficient for their catalysis reaction. This is a material that was made that they were trying to figure out the grain boundaries, and they suspected that zirconium, boron, hafnium, and carbon were going to be present in the grain boundaries because of how they were making this material, but it wasn't really obvious using EDS. So we looked at it under the electron microprobe, and we knew the grain boundary was somewhere between the two black blebs that are there. That's just Sharpie that they marked on the surface. And so I tracked through and found exactly where the grain boundary was based upon the small amount of those elements that I found there. This is a really cool project that was added in manufacturing, and they were figuring out methods to do welding for these joined materials that were additively manufactured. And the top one, it's pretty obvious where the join is, and they theorized that the nickel and chromium content would be higher on one side and lower on the other. And sure enough, you can see a very sharp boundary there where the two drop off, and there's no change in the carbon content across the two materials. And at the bottom, they had a really hard time figuring out where the weld was. There's not much contrast there. So I did find it, and they were expecting to see that there was a sharp increase in carbon at that weld. And that's what you can see on the bottom left, is that there is an increase in carbon at the weld area, and that the chromium and nickel vary not as much, but as expected between one material and the other. Some examples of some quantitative analysis. This is a lot of times I was doing stuff for homogeneity, where they cared about the indium lead ratio and the magnesium niobium ratios. And so I was tracking in two different directions. These are boules of crystals that were grown, and I would get a whole bunch of these at a time that I would have to do these analysis for, to check to make sure that the ratios weren't varying more than a specified amount in either direction of growth. And so you can see some, examples at the bottom. You can see in the horizontal and vertical direction that they are, the indium lead is definitely exact in both directions, and the magnesium niobium within error is also exact. This was a challenging example, as I mentioned, because of your activation volume. You have very large difficulty looking at nanometer scale compositions, but I figured out a way to do this. XPS was not giving the correct results that they were expecting. They were just showing a 1-to-1 ratio, and they were expecting it to be either 3 or 2.5, and they wanted to know which it was. So I figured out a way to vary the electron beam to penetrate at different depths, and then back out the compositions based upon that. And through that, I was able to show that the ratio between bismuth and niobium was indeed 2.5-to-1 as they were expecting it to be. This was an experiment where they were trying different methods of making a material, a ceramic material, and they had a reference from 2017 that they really liked, and they wanted to recreate that, but they had lost the specs for how to do it. So they were trying a bunch of different methods, and so they kept bringing me examples, and I kept analyzing them in order to find which composition matched the ceramic that they were expecting. Mapping is fun because it's colorful and pretty. So this is an example of a bronze where they were looking at the green structure and the green boundaries and seeing where the different alpha phases, and I forget what all phases there are. There's 3 different ones, I think, but you can tell by the relative concentration of the elements. And when you're looking at mapping, red means very high concentration, blue is very low concentration. So you can see in this, obviously copper is going to be really strong, but the nickel and the iron and the aluminum show very clearly where the different phases are in the bronze material. This is a geological example where they're looking at material from volcanic fields, and the zoning of different elements can tell you a lot about the thermal history of the volcanic regions. And so you can see in both cases where you get exsolution and zonation happening in these particles, and then you can actually do diffusion profiles across them and then figure out timescales and relative heat and things like that. This is a meteorite example, and this was it took a lot of mosaic mapping in order to map the entire thing. It looks very pretty. And then we wanted to look at the chemical composition. So we mapped a bunch of different elements and saw where the compositions were. And then what you can do is you can actually pull out the different phases to identify where in the what the distribution is in the different phases, and that tells you what type of meteorite it is. And so this was a project that was done and then published to analyze what type of chondrite it was. This is one of my favorites. This is where for one of the students' PhD work, he was doing this duplex steel, and he was doing EBSD, which is, so the first column is just regular backscattered imaging. The second column there is the EBSD, so he could see the phases, orientations, things like that. And then he was doing EDS at the same time in the last three columns. That's chromium, molybdenum, and nickel. And yeah, he got okay results from EDS, but he brought it to me and said, hey, can you get anything better from this to get more detail from the chemical composition? I said, sure, no problem. So this is the ROT sample, and you can see along the top is the original data that he had. And then I mapped the various elements, and you can see very clearly compared to the EDS imaging, what the structure looks like very clearly. This is the next one where, again, you can see very strong, grains and composition. And if you look at the nitrogen, you can even bring out the nitrogen a little bit with WDS that you couldn't do with EDS at all. And then when he looked at this, he could see that there was silicon particles scattered throughout the sample, and that was quite interesting because they didn't know that. And then once you do the further annealing and do the HIP process, that's the silicon actually just goes away, and so you don't see those particles spread around like you do. And so this was a very nice addition to his thesis. This was one that was brought to me, and they were making, this was for a high-end rocket nozzle. And they were seeing these black specks when they were imaging it in the SEM. And they thought it was a carbide inclusion. So they brought it to me, but if you see on the right, that's just noise. There's the highest count number there is 5, and that's nothing. That's just noise. And so I said, nope, those are not carbides. So what are they? Turns out that they're contaminants of titanium. And so looking back at it, so this is an additive material, and it turns out that the user prior to this particular material had used titanium in their process and had not cleaned the nozzles properly. And so little particles of titanium got trapped in this material. So they were able to clean out the titanium and then reprocess and eliminate those specks. Let's see, so here's some combination stuff. This is working with some cement samples. And this was part of a thesis project also, where we were doing a bunch of different, we did SEM, EDS, WDS, and then brought out some quantitative analysis also in order to get specific compositions to show that this particular cement that they were making for an application to be used in a space application. So they were able to get the composition that they needed. Here's one that these are inclusions in another type of material that was made, and they wanted to track the diffusion in these particles to figure out the growth rates and how to eliminate them from their process. And so we could, on the right, we were able to do very, very good diffusion profiles for these so that they could back out the data. So that's all I have at the moment, but I am happy to take questions.
Well, thanks for the talk, Kat. I enjoy it. So if people have some questions about the talk or questions for Kat in general about samples or anything, because she has just a huge range of knowledge, you can either go ahead, put those in the Q&A, that's the easiest place for us to find them, or also in the chat. If you have like a question you want to actually chat with her about, we can unmute people as well. I know there's a short question about the scale of the color on the maps, if that was just measure of concentration.
Yeah, so the scale, it's typically just that when you're just doing plain mapping, it's qualitative only. They're all collected at the same time. So they're relatively speaking, if you see something red, that's really high concentration. But if you can actually go in and map things that you know the concentration of, so that you can get a exact correlation, and then you can back out the, I didn't show that example, but there are some cases where we map some stuff and then we could actually pull out diffusion profiles from those maps because we knew what the concentrations were in different areas.
Most time when I'm talking to students, so we only have EDS here, is going to be a lot about trying to get quantitative information from EDS. And ends up, I try and say, hey, you can also use WDS. But I don't know if you want to talk a little bit about trying to do quantitative in EDS, and then also for any quantitative stuff, how you need to use standards.
Yeah, so EDS software in general has built-in standards. Those are fine for doing general ballpark ideas. However, if you need to get true quantitative analysis from EDS, you'd have to have standards that you know. So there's companies out there that make standard blocks that they know exactly what the composition of the materials are, and you can analyze those in EDS. You analyze the standards, you tell it what the composition is, it stores it as a standard, and then it can reference that instead of the generic ones that are already built in. And you can get quantitative analysis that's done very well in EDS if you're careful about doing your standardization. And you have to make sure everything's the same. So you have to make sure your current is the same, your accelerating voltage is the same, and you're looking at it in the same size, things like that. But if you're doing a one-to-one comparison and you've used a standard, then yes, you can get good quantitative data.
And WDS is somewhat similar, right? You do a similar kind of thing, but you get a lot better sensitivity.
Yes, we have a lot better sensitivity with WDS. WDS, you cannot just analyze something without, you have to have a standard or you don't get anything. It just gives you counts, and that doesn't tell you anything. Because we don't have built-in standards for WDS. So WDS, the first thing you do every time you're looking for quantitative analysis is you analyze your standards and you tell it what the standards are that it's comparing to.
And I saw a question about, they asked how fast is the technique compared to EDS? They take 30, 50 minutes for some of their EDS maps, and they're wondering kind of the comparison. So I think it'd be, yeah, good to talk about that. And then also like efficiency and wavelength range and all that kind of stuff between the two.
So you're always going to play this game of speed versus accuracy. EDS mapping is pretty good because it's quick and you get really good qualitative information very, very quickly. But WDS takes about, I don't know, 6 or 8 times longer to do. A typical map, just done what I call a quick map in WDS, takes about an hour. It's about the fastest you can do a map. And you get really nice maps, obviously, from WDS, but you're going to be playing the time game about how much time you're spending on the instrument and the same holds true for doing quantitative EDS versus quantitative WDS. It takes a lot longer. So, people that just need ballpark ideas, EDS is fine because it's quick and it's easy. With WDS, you're looking at spending a minimum of an hour or more, depending on the level of detail you need. For instance, just the setup alone is, with the standards, is probably close to an hour.
Cool, thanks.
Does that, I'm happy to clarify more. I actually have a presentation on problems and pitfalls of EDS analysis.
Yeah, and that's the other part that, yeah, I'm always talking to students about with EDS and that. So I see another question. How did you figure out the features were not carbides and they were titanium? Detecting carbide is challenging with EDS. What's the reason of selecting titanium for detection?
I just randomly picked a whole bunch of different elements and I chose things that I thought might possibly be there. It actually took quite a while to figure out that it was titanium because I looked for chromium, I looked for iron, I looked for, I don't even remember all the stuff, nickel. It was a long list of things that I went through, and it wasn't until I stumbled on titanium that I found that's what it was. Now with EDS, if EDS was a little more focused and able to distinguish better, that would have been done a lot quicker because you can collect all the elements at the same time. But with WDS, it took a while.
What is the spectral range usually for WDS it can collect at one time?
So most electron microprobes have 5 wavelength detectors on them. Some of them only have 3 or 4, but all the ones I've used have had 5. So you can only collect 5 elements at a time. So if you're looking at something that has 10 different elements, you're looking at least 2 different passes, which is where the time just expands upwards from there. So if you're looking at something simple that only has a couple of elements in it, it's not bad. But once you get beyond 5, then you have to do more than one pass.
I was thinking of some projects that I've had recently where people are trying to look at rare earth elements. There's not too much we could do with the samples with EDS just because that's where any of our sun peaks are. We're never sure what's going on there. I saw some cool stuff in CL, but it's hard to actually identify what the rare earth elements are in there. Have you done much with that?
I actually did. That was one of my last projects that I did before I left Penn State, was doing rare earth elements, where they were looking for coal mine recovery. So they were trying to find from the basically the cast off coal stuff, they wanted to find the rare earth elements in there and figure out which minerals they were associated with. And you can't do that in EDS. There's just way too many overlaps. So I was just doing a ton of different wavelength scans and able to pull out exactly what rare earths they are. They're very distinguished. There's a few that are tricky because they overlap a little, but for the most part, you can pull out exactly what rare earths are in a material.
Yeah, well, I don't see any more open questions right now, but we'll hang out for just a minute or two, see if anyone comes up with other questions. Yeah, Kat, I haven't chatted with you in a while in general, but what are you mainly working on at Morgan now, as far as analysis and everything goes?
I haven't done a ton of analysis lately. I'm mostly doing I'm trying to remember how much I'm allowed to talk about. I'm looking at a material that's going into parts that go into electric cars.
Cool.
And we're trying to create a new material that will perform better than the current stuff. And so it's just a lot of mechanical testing right now is mostly what I'm doing, is running these parts on an apparatus and seeing how they perform. So a lot of basic chemistry coming up with the materials, but I mean, I did do some failure analysis characterization where we were trying to figure out what was causing these parts to break. And so I had to go over to MCL and do some analysis using the EDS to try to figure out what caused the failure, and I was able to.
Nice, cool. I saw another question that came in as well. So they're asking, since the signal data is produced both by electrons, does interaction volume differ greatly from EDS? Are they probe energy pitfalls?
Not sure. So the activation volume is the same between EDS and WDS because the X-rays are coming from the same volume. If you're doing a one-to-one comparison using the same accelerating voltage, so like let's say you use 15 kV, which is a typical accelerating voltage, the activation volume is going to be exactly the same whether you're using EDS or WDS. So there's no difference there. I'm not sure about the second half of the question. I mean, the main pitfall is just making sure you're not hitting things that are under the surface that you don't know are there, because you are sampling from like a micron or two deep. And so if you have like inclusions that may not be visible on the surface, you could accidentally hit some inclusions. So always take multiple data points to make sure you're getting a good spread of data so that you can look at it instead of just taking one point.
Yeah, I think that answered that question. Yeah, I think we're just about out of time. If anyone has any quick questions, they can post those up. Otherwise, thanks again, Kat, for making time for the talk. I enjoy these talks quite a bit with hear about the techniques a little bit more, talking to you, Kat, about these. So if you have other questions, I'm sure Kat would be more than willing to answer them a little bit in email form or anything.
Oh yeah, absolutely. Feel free to email me, and I'm happy to do that. Yep.
Cool. Okay. Thanks again, and we'll see you guys starting next semester. Bye.
Thank you.